Hello friends, in this video we will see Bode plot for single pole system. So this is basically a revision class for Bode plot or for single pole system. So first thing is why single pole system is very much important. Why? So because single pole systems are stable, we will see this stability concept, but just I would like to tell you single pole system are stable. Any system we design, any amplifier, buffer or any system, and if it is working in feedback, then we try to make it close to single pole system so that it will be stable system. We will see in future videos uh, what is the concept of stability, and we will see when a system get unstable. So our focus whenever we design any system with feedback, we try to make it close to single pole system. In that case only phase shift is 90 degrees. So here because this systems is stable, that's why we design any system single pole or close to single pole, because if we are designing any system in feedback, okay, we want our system should be of a single pole because it gives phase shift equals to 180, oh sorry, it gives phase shift of 90 degree. And for unstable system, if phase shift is greater than 180 degree, for unstable system, or you can say greater than equals to 180 degree, then system is unstable, and we have ringing in our system. So it is important to make our system close to single pole system, that is phase shift is 90 degree, not more than that. Actually we have a phase shift more than that, and uh, but we uh, and at 90 degree, if phase shift is 90 degree or close to 90 degree, then our system is slow. We will see this concept further in further videos. And if if we are having more phase shift and phase margin is say uh, 60 degree 50 degree, then system is bit faster as compared to phase margin is 90 degrees. So there is a concept of phase margin as well. So phase margin basically we consider 180 minus whatever phase shift. Okay, so if single pole system is 90 degree phase shift, then phase margin is 90 degree. So if phase margin is 0, means phase shift is 180 degree. So this will make system unstable and we get ringing. So our main focus, main purpose when we design a system is that we want a stable system. For that phase margin should greater than 45 degree, so that we have some settling like this and system is fast enough. And in case of 90 degree phase margin, our system settle like this. So we will see this phase margin stability concept in upcoming video. Now let's start So this is basically I am telling you importance of single pole system, why we should know, we should study single pole system, why it is important. Um, so okay, let's understand single pole system. It's Bode plot, gain bandwidth product. Say this is our single pole system. So this is RC. Say this is some gain, DC gain. So this is uh, our system. Say HS. So HS is given by 1 by 1 plus S by omega p. Omega p is pole frequency, which is minus 1 by RC, and A naught is DC gain of this system. So this is input, this is output. Okay, now magnitude response is given by 1 by 1 plus omega upon omega p square root. We represent our Bode plot in dBs. So magnitude in dB is given by, okay, so here this is A naught DC gain. I forgot to add this. Okay, now so this is 20 log A naught plus 20 log 1 by square root 1 plus omega upon omega p square. So this is our magnitude response, and in this we consider different cases. So case 1, omega is much less than omega p. If omega is much less than omega p, this term is 0 and it will get 20 log 0, 20 log 1, and this term will be 0. So we will get magnitude in dB equals to 20 log A naught. Okay, so this is our DC gain. Okay, so for omega less than omega p, we get DC gain in dBs. Now let's consider case 2, in which omega equals to omega p. In this term is omega equals to omega p 1 by square root 2. So it will be magnitude dB response will be 20 log A naught. Okay, so this will be minus 20 log square root 2. This will come as 3 dB. 20 log A naught. So this is magnitude response is 20 log A naught minus 3 dB. So this is also known as omega p, also known as minus 3 dB frequency, because at this frequency my actual gain is reduced by 3 dB. Now let's consider case 3, when omega is much greater than omega p. So if omega is much greater than omega p, then this second term is much greater than 1, so we can ignore 1. So it will become like magnitude in dB 20 log A naught plus 20 log omega p minus 20 log omega. So you can consider it as a straight line. So this is mx, this term is like c, this is like y. Okay, now suppose omega we increase by 10 cross, then this term will be minus you can say 20 dB, and this shows that gain is reduced by 20 dB. So it means if we are increasing frequency by 10 cross, gain is reduced by minus 20 dB. So this gives us gain roll off for single pole system by minus 20 dB. Now let's consider case 4, in which case we will give gain bandwidth formula. So in this case, now let's consider this. So omega equals to omega UGB, and that omega UGB means unity gain band